Hi, everyone, and welcome to the Molecular Munch. This is our idea from Hopefully Nothing Goes Boom, where we wanted to take a bite-sized chunk out of one of the molecules that we talk about each month and see what comes up in conversation when we just chat about it. So my name's Phil. I do the graphics and run some of the stuff on the website, and Marcus writes the articles himself. So we know each other from our PhD days when we studied chemistry. So hopefully we know roughly what we're talking about. But that is absolutely no guarantee that what we say is going to be true or entertaining in any way. But Marcus, you've picked this month oxalic acid. Do you want to just tell us a little bit about why you've picked that molecule?
Yeah, so hi Phil and hi everyone else. So oxalic acid is one of those molecules that you're likely to have encountered on a regular basis, some more so than other. And I think it's also one that you've probably heard about in other forms, but not quite been aware of it. So the real inspiration behind oxalic acid was where it's naturally found, which is rhubarb is the most common source. So you might well be aware that people say you shouldn't eat the leaves of the rhubarb plant because it can be poisonous. And the real sort of poison, if you like, behind that is the oxalic acid, which is found in rhubarb. Now, what was quite interesting when we started to look into this is whilst rhubarb is, if you like, the poster food for oxalic acid, it actually occurs in higher amounts in other leafy foods and indeed herbs. And one of the worst culprits is actually spinach.
So, of course, as soon as you told me that I needed to draw spinach, there's only one thing on my mind, and that's Popeye.
It's Popeye, exactly. Popeye, the sailor, spinach-loving hero, is not just getting his sort of share of iron, which is, you know, what people often attribute spinach to, but he's getting a decent amount of oxalic acid in him.
Would it make him stronger?
Very unlikely. And in fact, oxalic acid can be poisonous. You know, those stories are indeed true. And in small amounts, you know, oxalic acid is perfectly normal. So as much as your viewers might want some excuse to not eat their veg, there's certainly no reason to use that as an excuse for avoiding spinach or rhubarb, or indeed some herbs like parsley and chive, which have high concentrations of...
I knew there was a reason I avoided parsley.
Yes, yeah. It goes well with a nice white sauce and some artificial potatoes. But anyway, now, one of the main problems with oxalic acid is when it reaches your kidneys. So just to give perhaps a little bit of the chemistry and the structure behind oxalic acid to help understand why this is a problem in your body. So oxalic acid, I think you have the structure of it somewhere.
There you go.
First of all, it's very pleasing on the eye because it has a symmetric appearance to it, which I don't know you feel, but I always like things that look symmetrical or have some kind of pattern or symmetry to them.
Ooh.
But we call it an acid. Now, its acidity comes from the fact that it contains hydrogen atoms that can dissociate, which is the chemical, you know, the scientific term, or you could think of it as can readily detach themselves or fall off if you want something a bit more.
That was always the way I used to say it. Yeah.
Yeah, you know, it's
fell off.
Probably the most blunt, but in some ways the most direct and easy way to consider what an acid is. Now, oxalic acid belongs to a family of molecules called carboxylic acids. And they're so-called carboxylic acids because they contain the group you can see there. So you've got a carbon atom, which has a double bond to one oxygen atom, then a single bond to a second oxygen atom, which also is then bonded to a hydrogen atom. And it's this hydrogen atom that when it falls off or dissociates is what makes it acidic. Now, some of the more observant amongst you might have already noticed that oxalic acid contains two of these groups. two such groups, and as you might expect, both of those can dissociate, which makes it a diacid or a dicarboxylic acid.
This is typically where chemical names get quite difficult to pronounce, isn't it?
Yes, exactly. Now, why is this important? Well, because of the oxygen atoms and various other bits, it does give some properties to this molecule. So it's easily dissolvable in water or solvents such as ethanol, which is commonly known as just normal alcohol.
Mm-hmm.
And what happens is when it's dissolved in, say, water, these two hydrogens come off, you form an anion called oxalate. Now, this anion is particularly fond of metals. And I'm not talking necessarily about, the lump of metal you might see structures built out of, or, lumps of gold. I'm talking metal ions. I'm talking about, tiny atoms that, might exist within our bodies, for example, within our blood. Obviously, there are certain amounts of these in everyday things. Now, the problem is when you have this oxalate in our bodies, in the bloodstream or going to the kidneys, there is an ample supply of calcium in there, amongst other metals, but it has a good fondness for calcium. And when it finds calcium, it binds to it, they're attracted to each other, and this causes it to, we say, precipitate. What that means is it comes out as a solid. Now, you can probably imagine that obviously our blood vessels or other channels in our body, usually contain fluids, and the idea of having something hard suddenly appear in them is not ideal. And this is a particular problem with too much oxalic acid, is you can form calcium oxalate, which is a solid substance which gets formed within the kidneys. Now, these are small enough that they can still be obviously transported through our bodies, but at some point they have to be removed. And if you've ever suffered from a condition known as kidney stones, which is what calcium oxalate is, you'll know that one of the main ways of removing them, and the most painful way, is to pass them through a very delicate area of our bodies.
Very sensitively put.
Very sensitively put, very sensitive, and obviously, even though these stones might be millimeters, we're talking tiny amounts, they are not very pleasant to pass at all. That's in small amounts. Now, the problem is if you have a lethal dosage of oxalic acid, which is possible, then this sort of crystalline, this solid calcium oxalate obviously builds and grows within the kidneys and can ultimately lead to kidney problems.
Okay.
Now,
we don't want that, but I mean, you say a lethal dose is possible, but it's not really going to be possible with the kinds of amounts that the average person is going to be eating of rhubarb leaves or spinach, is it?
No, there's two important points to that. The first is that the amount you would have to eat, so take spinach. We said earlier spinach has quite a high amount, probably slightly higher than, say, rhubarb. But even then, we did a very rough calculation, and, you would have to eat 4 kilograms of spinach raw for that to be a lethal dose. And even then, you would probably have to eat it within quite a short sitting. And I know Popeye enjoys his spinach. I'm sure there are many spinach fans out there, but that is a lot of spinach to eat.
Yeah, and you said that's raw. So is it less of a problem when things are cooked?
Yeah, so most of the values that you could typically find for the content of oxalic acid are in their raw form. And like many sort of leafy sort of plants or herbs or that, they're usually exposed to some kind of cooking, heat, steam, other things, which can actually remove some of the oxalic acid from them. So even if you were to cook 4 kilograms of spinach, unless you were to eat it all and drink all the water that you were, say, boiling it in, or all the liquid that came out, you're unlikely to probably have a lethal dose.
Okay, well, I mean, hopefully that's reassured people to go out and have their Sagaloo later. Don't want to put anyone off that. So people are probably going to have eaten some oxalic acid at some point. Do you reckon it's useful for anything else? Have you come across any other uses for it while writing the article?
So something that's been well known is when you go to cook, say, a piece of rhubarb, if you cook it in aluminium pans or even some sort of old-fashioned iron pans, it can actually remove like a layer of the metal from the bottom of the pan, which, whilst it leaves you with very clean, shiny pans, ends up turning the food brown and giving it quite a horrible flavour to it. And obviously that is because of the oxalic acid that's present and its love for all things metal. Now, again, not to worry people, this isn't the case if you use a pan that's been coated, you know, say particularly in a non-stick surface or some other kind of metal, but this has been put to good use, and oxalic acid is used as a rust remover to sort of clean rusted objects in a similar way that it can obviously clean your pans or the sort of aluminium iron pans. It can be used to remove rust.
So it sounds like it's quite a strong acid then.
When it comes to acids and bases, everything is relative, which sounds like a bit of a get out of jail sort of answer, but we have many ways of classifying acids and the corresponding bases. And when we talk about the strength of an acid, to chemists, what that means is how easily and how readily that hydrogen dissociates from the molecule.
It falls off.
It falls off. So hydrochloric acid is something everyone's familiar with, whether you remember it as a current student, whether you remember it from, you know, those horrible days in the lab 40, 50 years ago, whatever. We call that a strong acid because the hydrogen and the chlorine almost always dissociate. The hydrogen always comes off most of the time. Oxalic acid is a little different. As a carboxylic acid, that hydrogen doesn't easily come off, and it might only come off, say, if you had 100 molecules of it, you find that it's only a very small number that actually dissociate. Obviously, with oxalic acid, you've got these two hydrogens, which obviously doesn't quite double the effect, but it's simple enough to think that the more you have of something that can be acidic, the more acidic it might be.
Sure.
So relatively speaking, compared to a carboxylic acid, we're all familiar with vinegar, which is ethanoic acid or acetic acid. Oxalic acid is relatively strong. But I think if you were to put, you know, some rhubarb or cook some rhubarb and sort of dip your finger in the resulting liquid, you know, you're not going to have horror stories of it dissolving away. So it's strong as far as a chemist might consider a carboxylic acid, but far, far beyond the more familiar ones like sulfuric acid or hydrochloric acid.
Absolutely. And if people are interested in sulfuric acid, you wrote an article about that a good few months ago, so people can go and check that one out. I think that's everything we need for oxalic acid here, Marcus. Now, the last question I'm going to ask you, would you take, after having written all of this article and done all this research and chatted about it just now, would you take a Munch out of this molecule?
Well, Phil, I will put the disclaimer out there, as every good sort of chemist should, that you should never eat or drink any chemical or anything in a lab. So just to satisfy all those who might be horrified to hear of such a thing. But as it's found in rhubarb, and as obviously that's the main component, or spinach, I would happily take a bite out of some spinach or some rhubarb, and therefore, yes, I would have a munch of oxalic acid.
Lovely stuff.
You, because I don't want to pass kidney stones.
Yeah, not too much. And we certainly don't want to be going to the toilet after Popeye, because I think he's probably going to be a bit uncomfortable.
One of many reasons, yes.
Well, yeah, quite. So I think that does it for this month, and we will be back next month. I'm sure all molecules that we pick end up being about food in some way anyway, whether it's cheese from the moon or whether it's any other of the tasty molecules that we've looked at. So that's it for this month, and I hope you'll join us again. It's goodbye from me.
And it's goodbye from me.
Take care, everyone. Bye.
Bye.